Quantum mechanics is often described as one of the most confusing subjects in modern science. But why is that? To begin with, quantum mechanics deals with the tiniest particles in our universe, things like electrons and photons. Unlike the objects we see every day, these particles behave in ways that seem to defy common sense. For example, they can be in more than one place at once, or change their behavior just because we observe them. This is a far cry from the predictable world of classical physics, and it's the first reason why quantum mechanics can feel so baffling. The heart of quantum mechanics are particles so small that we can't see them with the naked eye. These particles don't follow the same rules as larger objects. Instead, they exist in a world where probabilities rule, not certainties. This means that instead of knowing exactly where a particle is, we can only predict the chances of finding it in a certain place. This idea alone is enough to make anyone scratch their head, because it challenges our everyday experience of the world. One of the most famous concepts in quantum mechanics is wave-particle duality. This means that tiny particles like electrons can act both as particles and as waves. Imagine throwing a baseball and seeing it behave like a ripple in a pond at the same time. That's the kind of weirdness we're talking about. This dual nature makes it hard to picture what's really happening at the quantum level, and it's a big reason why quantum mechanics feels so strange. Another key idea in quantum mechanics is the uncertainty principle, introduced by Werner Heisenberg. This principle says that you can't know both the position and the speed of a particle exactly at the same time. The more precisely you know one, the less precisely you know the other. This isn't just a limitation of our measuring tools, it's a fundamental property of nature. This uncertainty is deeply unsettling for many, because it means there are limits to what we can know about the universe. Superposition is another mind-bending idea in quantum mechanics. It means that a quantum particle can exist in multiple states at once until it is observed. For example, an electron can be in two places at the same time or spin in two directions at once. Only when we measure it does it choose a state. This concept is famously illustrated by Schrödinger's cat, a thought experiment where a cat in a box is both alive and dead until someone looks inside. Superposition challenges our basic understanding of reality. Quantum entanglement is what Einstein famously called spooky action at a distance. When two particles become entangled, the state of one instantly affects the state of the other, no matter how far apart they are. This seems to violate the idea that nothing can travel faster than light. Entanglement has been proven in experiments, but it's still hard to wrap our heads around. It's another reason why quantum mechanics feels so mysterious and confusing. Quantum mechanics, the act of observing, can actually change what happens. This is known as the observer effect. When we measure a quantum system, we force it to choose a state, collapsing all the possibilities into one outcome. This idea is so strange because it suggests that reality depends on whether or not we're looking. It's a big departure from classical physics, where things happen whether we watch or not. Like classical physics, which deals with certainties, quantum mechanics is all about probabilities. Instead of saying exactly where a particle is, we can only give the odds of finding it in a certain place. This probabilistic nature makes it hard to predict outcomes with certainty, and it's a big reason why quantum mechanics feels so unpredictable and confusing. Quantum mechanics relies on advanced mathematics, including complex numbers and abstract equations. For many people, the math itself is a barrier to understanding. The equations describe probabilities and wave functions, not concrete objects. This mathematical complexity adds another layer of confusion, making it hard for non-experts to grasp what's really going on. Any results in quantum mechanics go against our intuition. For example, particles can tunnel through barriers, appear to communicate instantly, or exist in multiple states at once. These results don't match our everyday experiences, which makes them hard to accept and understand. This counterintuitive nature is a big reason why quantum mechanics is so confusing for so many people. In classical physics, we can often picture what's happening, a ball rolling, a planet orbiting, but in quantum mechanics there are no simple visual models. The behavior of particles is described by abstract math, not by pictures we can draw. This lack of visual representation makes it even harder to understand what's really going on at the quantum level. Quantum mechanics has several different interpretations, like the Copenhagen interpretation, many worlds, and pilot wave theory. Each offers a different way of understanding what's happening at the quantum level, but none has been proven to be the right one. This variety of interpretations adds to the confusion, because even experts can't agree on what quantum mechanics really means. Measurement plays a unique role in quantum mechanics. Unlike classical physics, where measuring something doesn't change it, in quantum mechanics, the act of measuring can fundamentally alter the system. This means that what we see depends on how we look, which is a deeply unsettling idea for many people. It's another reason why quantum mechanics is so hard to grasp. Schrödinger's cat is a famous thought experiment that highlights the weirdness of quantum mechanics. In this scenario, a cat in a box is both alive and dead until someone opens the box and looks. This paradox shows how quantum superposition leads to outcomes that seem impossible in everyday life. It's a vivid example of why quantum mechanics is so confusing. Quantum tunneling is another strange phenomenon. It allows particles to pass through barriers that should be impossible to cross, according to classical physics. This effect is used in real-world technologies like tunnel diodes and scanning tunneling microscopes, but the idea that particles can tunnel through walls is hard to accept, adding to the confusion around quantum mechanics. At its core, quantum mechanics is fundamentally random. Unlike classical physics, where everything happens for a reason, quantum events can occur without any clear cause. This randomness is built into the very fabric of the universe, and it's another reason why quantum mechanics feels so unpredictable and confusing. Nonlocality is the idea that particles can affect each other instantly, no matter how far apart they are. This goes against the idea that nothing can travel faster than light. Non-locality has been demonstrated in experiments, but it's still hard to understand. It's another example of how quantum mechanics challenges our basic ideas about space and time. One reason quantum mechanics is so confusing is that it's so different from classical physics. In the classical world, things are predictable and follow clear rules. In the quantum world, things are uncertain, random, and sometimes seem impossible. This clash between the two worlds makes it hard to understand how quantum mechanics fits into our everyday experience. Double-slit experiment is a classic demonstration of quantum weirdness. When particles like electrons are fired at a barrier with two slits, they create an interference pattern as if they were waves. But if we watch which slit they go through, the pattern disappears and they act like particles. This experiment shows how observation changes reality, and it's a key reason why quantum mechanics is so confusing. Quantum mechanics isn't just confusing, it's also powerful. Quantum computers use the principles of superposition and entanglement to solve problems much faster than classical computers, but the way they work is so different from traditional computers that it's hard to understand. This new technology is another example of how quantum mechanics challenges our usual ways of thinking. Quantum field theory is an advanced part of quantum mechanics that describes how particles interact with fields. It's even more abstract and mathematical than basic quantum mechanics, and it's used to explain things like the Higgs boson and the forces of nature. The complexity of quantum field theory adds another layer of confusion for anyone trying to understand the quantum world. In quantum mechanics, there are no clear boundaries between particles and waves or between objects and their environments. Everything is connected in ways that are hard to define. This lack of clear boundaries makes it difficult to draw simple conclusions, adding to the confusion. Quantum mechanics doesn't just challenge our understanding of physics, it also raises deep philosophical questions. What is reality? Does the universe exist when we're not looking? These questions go beyond science and touch on the nature of existence itself. The philosophical implications of quantum mechanics are a big part of why it's so confusing. Our everyday language isn't designed to describe the quantum world. Words like particle and wave don't fully capture what's really happening. This limitation makes it hard to explain quantum mechanics in simple terms, adding to the confusion for anyone trying to learn about it. Quantum mechanics is full of paradoxes, situations where the rules seem to contradict each other. From Schrödinger's cat to the EPR paradox, these puzzles show just how strange the quantum world can be. Paradoxes make it hard to know what to believe, and they're a big reason why quantum mechanics is so confusing. Experiments in quantum mechanics often produce surprising results. Sometimes, particles behave in ways that no one expected, forcing scientists to rethink their theories. These surprises keep quantum mechanics exciting, but they also add to the confusion because the rules can seem to change without warning. Despite its confusion, quantum mechanics has led to amazing technologies like lasers, MRI machines, and quantum computers. These inventions rely on quantum principles, even if we don't fully understand them. The practical success of quantum technology shows that the theory works, even if it's hard to grasp. Learning quantum mechanics takes time and effort. The concepts are so different from what we're used to that it can feel like learning a new language. Many students struggle with the abstract ideas and complex math, which adds to the sense of confusion. But with patience and practice, it's possible to gain a deeper understanding. Quantum mechanics is still a young science, and new discoveries are being made all the time. As scientists learn more, our understanding of the quantum world continues to evolve. This ongoing process means that confusion is a natural part of exploring the unknown, and it's what makes quantum mechanics so fascinating. In the end, the confusion surrounding quantum mechanics is part of what makes it so intriguing. The mysteries and paradoxes challenge us to think in new ways and push the boundaries of what we know. While we may never fully understand the quantum world, embracing its mystery can inspire curiosity and drive scientific progress. Quantum mechanics reminds us that the universe is far stranger and more wonderful than we ever imagined.